0 and 4 are two critical numbers of this function. So far, I still have to look at this. Okay? So now, I take a look at the derivative, right? The derivative of this function was 3x squared minus 12x. And I ask myself, are there any values of x that would cause this function to malfunction, to not work? Are there any domain restrictions on this? No. You can plug any number you want into this, right? Anything. You're never going to have division by 0. You're never going to have like a square root of a negative number, right? There's no trig functions involved. Sometimes some of the trig functions have domain restrictions. So I have no issues here. So basically, I have nothing from this, right? Nothing contributes over here. Hey, I noticed this on the test. I forgot to mention this. This is off topic, but I wanted to mention it. So when I write the number 0, right? That's the number 0. I've seen some students that will write that for 0. And usually this means that you have maybe some military background. This is the way we write the number 0 in the military. But in mathematics, this is not the way we write the number 0. This is actually something called the empty set. Okay, this is called the empty set. And this is the number 0. So let me try and explain what I mean by this. Imagine I have a basket, okay? And inside of that basket, I put a bunch of numbers, okay? You see all the numbers sitting in the basket? Okay. If I have this basket, let me empty it. Hold on, let me empty it. All right, so now I have the basket and I put the number 0 in there, right? I put that number 0 into the basket. This is the way I'd write that. The set 0. This is my basket and it has 0 in it, okay? Now, what if I take that basket and I dump it out? There's nothing in the basket now, right? How do I write that? Well, I could write it like this, or I could write this. This and this mean the same thing. It's an empty basket, but this is not the number 0. It's like this is a dog and that's a cat. They're totally different things, so you can't be saying that that's the number 0. Now, I'm not going to take off. I'm just saying that, in the military, I understand why they do it, so you don't confuse it with O, right? Do y'all know why the military, they use niner for the number 9 instead of 9? Like if you verbally are saying the number 9, you say niner. Any military? Sounds like 5. 9 can sound like 5. It actually comes from World War II, and it comes from when we were using radio communications, and you would sometimes accidentally pick up other transmissions, and the Germans Germans spoke German. And the word 9 means no in German. So you could hear someone say a German radio communication and they're saying no, you hear 9 and then you change your heading to 9 and then you go drop the bomb on the wrong. It's just so there wasn't any confusion between the German word no and the English number 9. All right, random useless information. Okay, so what are the critical numbers? 0 and 4, we're done. All right? Now, we're going to do more of these, all right? But I need to get to the next idea. The main takeaway for you is this. Critical number is any number that makes the derivative 0 or the derivative not exist, so long as that number or those numbers are in the domain of the original function. Now, what can we do with it? Well, we have Fermat's theorem. And this is a big theorem. We don't need to memorize the theorem. We just need to know what the consequences of this theorem are. This theorem says, if your function has a local maximum or some local minimum at some point. So imagine you have a function, it goes up, you have a hilltop, or it goes down, you have a valley, something like that. This theorem says if you have a hilltop or valley at some point C, then guaranteed 100% that C must be a critical number. Which is saying that peaks and valleys occur either where your derivative is 0 or your derivative doesn't exist. So I'm going to show you, I'm going to draw a picture for you. All right. Do you all see a local max? And by the way, this continues, okay? Do you all see a local max? Yes? Right here? Tell me about the derivative at that point. The derivative is 0. Do you all agree? Do you see a local minimum? Okay, tell me about the derivative at this point. 0, right?
Thought the going down to infinity, would that be where it doesn't exist?
Well, here, no, this, we wouldn't have a local anything, because it would just keep going.
Okay.
Oh, you're talking, no, I know what where the derivative doesn't, I'm going to show you. I'm continuing this.
Right.
You ready? That's a cusp. That's a cusp, right? Is it a local maximum? Yes, that is the highest point locally, isn't it? Okay, what's the derivative doing there? It doesn't exist, right? The derivative doesn't exist at cusps or corners. But it's a local max, right? Do y'all see what's happening here? Fermat's theorem says if you have a local max or a local minimum, I guarantee, or the theorem guarantees that the derivative either is 0 there or it doesn't exist, one or the other. Okay? Let's see, now you have to be careful with this. Watch this. This one is the one that makes people get confused. All right. Tell me about this point right here. What is the derivative there? The derivative is, it's flat, right? The derivative is 0, isn't it? The derivative is 0, but it's not a local max or min, is it? What does the theorem say? I'm going to put it back up here, because it's so important that you read this thing properly. If what? What's the condition? If you have a local max or min at a point, okay? If you have a local max or min at a point, then the derivative must be either 0 or doesn't exist. Is this a local maximum or minimum? No. Right? So this theorem does not say, this is the way people misinterpret it. The theorem does not say that if your derivative is 0 or your derivative doesn't exist somewhere, then you must be looking at a local max or min. That's not what the theorem says. The theorem says if you have a local max or min, then you can conclude that the derivative is either 0 or doesn't exist. It's not the other way around, right? Remember I gave you that example of living in Texas versus the United States, and you can't reverse it? This is that idea. If you live in Texas, then you're in the United States. You cannot say that if you're in the United States, then you're in Texas. Let me see if I can, yeah.
So wait,
Yeah,
so
yeah.
if it's straight, then
If it's what?
if we have a straight line like that, then do we have a local max?
No, there's no local max here. So this is a local max, right? And check it out. The derivative here is what? 0. Right here, this is a local minimum, right? And what's the derivative here? 0. What is this? A local max. And what's the derivative here? Derivative here doesn't exist. This is a nothing, right? It's not a local max. So I'm not even thinking about the theorem. Now, is the derivative 0 here? Yeah, but the theorem is talking about if you start with the local maximum, then you can conclude something about the derivative, not the other way around. Here's another way you can kind of look at this. What if I told you that I had a graph, right? What if I told you go to the value of 3 and I go here? What if I told you that the slope of the tangent line there was flat? Could you then conclude from that that it's a local max or min?
Yeah.
Would that be enough? If I just tell you that the derivative here is 0.
Oh, I know.
No, because I could draw this, couldn't I? And then it's not a local max or min. So having looking at the fact that it's just derivative 0 or doesn't exist is not enough for us to determine if it's a local max or min. All right, do you understand that theorem, kind of? So now what we're going to do that we've established those definitions and ideas is we are going to focus our attention on trying to find the max and mins on a function, all right? Just generally speaking, we're going to be trying to find the highest and lowest points on a graph. And we're going to break it into 2 different categories, all right? And yeah, so let me put here. Finding max min of functions. All right. This is supposed to be like, here are the two different scenarios. The first method, this is called the closed interval method. And the other one, the book doesn't call it the open interval method, but I do. This is called the open interval method. Burn this into your brains. If you're trying to find the highest and lowest points on a function, there are two different approaches. And they're not like two approaches where you get to choose. The problem will dictate which of the two you're going to use. The first method is going to be used when your function is defined on a closed interval. So you're going to use this method if your function starts and stops at 2 points. Then you're going to use that method. If your function doesn't start and stop at 2 points, if it does something, where you have more like arrows, then we have the different method for this, all right? And I will tell you right now that comparing these two methods, this one's the easy method, and this one's the hard method, all right? Hard is in, it's going to require a lot more work for us if we don't have a closed interval. Today is about this method, okay? Next class, we will do this method, and it's a different section in the book. It's not in this section. So what are we in, 4.1? 4.1 covers this method, all right? So this method right here is 4.1. That method over there is 4.3 and 4.4. Two different sections. All right, feel good? So I've never done this before. I'm going to try and explain the closed interval method visually first before I actually give you the method, all right? And try and show it visually. So everyone understand we're going down this method right here, okay? That's what we're going to focus on. All right, so here's how the closed interval method works. Let's see if we can deduce this logically here. Let's say someone gives us a function. Let's say it starts here at A. Let's say it ends here at B, all right? And let's say we have a continuous function, all right? To keep things simple, because if it's not continuous in there, then we lose a lot of these theorems, right? So we're given f on a closed interval, right? And f is continuous. I'm just going to put that, all right? So we're given some function, it's on a closed interval, and it's continuous. By the way, if I made this endpoint open, we can't use this method, all right? I have to have closed interval. Function must be defined at both endpoints. All right, so let's say we were trying to find the highest and lowest points. We know they exist, right? Why do we know they exist? It's continuous, right? I have to connect those two. We said earlier, there's no way to draw it without having some highest and lowest points. So we know it's got to exist. So how could we find it? Well, one thing we could do is we could find the critical numbers, couldn't we? Look, why don't we do this? Why don't we find the critical numbers? What would that tell me? Like, let's say I find some critical numbers. Would that tell me where I have highest and lowest points?
Yes.
Careful. No, but they could tell me where to look, right? Because doesn't the theorem say if you have a local max and min, if you do, they have to occur at these critical numbers, right? So what I can do is I can find all the critical numbers, and then I can actually compare those to the, whatever's happening at one critical number compared to the other critical number, what's happening to the function. And I can see which of them is giving me a higher and a lower value. So I could find the critical numbers, and then I could, so the critical numbers here, because we would kind of know this, we can see it here. I would have a critical number here, I'll call it C1, C2. I would have two critical numbers here, wouldn't I? So is C1, is this where we have an absolute max or no? That's not the highest point. How would I know that though? Like if I got this value, how would I know that that's not the absolute max? What I could do is I could plug this value into the function and see what y value it spits out, right? And then I could compare that to what happens at this one and where else would I need to compare it to? The two endpoints. It could happen that this is the lowest point and that's the highest point, right? So I'm going to find the critical numbers, right? That's the first thing I'm going to do. Find the critical numbers. Second thing I'm going to do is I'm going to evaluate the function f at the critical numbers. And when I say evaluate, I mean plug those numbers into the function, right? Plug them into the function. Plug them into the function. The third thing I'm going to do is I'm going to evaluate the original function at the endpoints. What do I mean by endpoints? I mean at the points A and B, right? Plug A into the original function, plug B into the original function. I'm going to look at all of those together. That's my final step. I compare, I compare answers from step 3 and 4, 2 and 3. Right, so I will have plugged the critical numbers into the function, the original function. I would have plugged the endpoints into the original function. I'm going to have a bunch of answers. I'm going to look at those answers. The biggest number I see is the absolute max, and the smallest number I see is the absolute min. So absolute max and the absolute min will come out of this, right? Let's do an example. That way we can clarify that a little bit more. And I have enough room to do it right here. Let's go back to the problem we just did. Right? I gave you that function. It was f of x was equal to x cubed minus 6x squared, right? Okay, and we have to put it on a closed interval. So let's look at it between -1 and 2. And let's find the absolute max and min. So I'm giving you a function there, right? It's a continuous function, right? A continuous function on a closed interval, and I want to know the highest and greatest, least value, highest, lowest value, absolute max, absolute min of that function. Okay? First step, what do we do? Okay, we did that step already, right? I'm put a check here. Didn't we do that already? What did we get, 0 and 4? Okay. Now, what are we supposed to do with those answers? Make sure they are in the domain of the function. Now, I've restricted the domain, haven't I? So are 0 and 4 in that domain? Well, 0 is, but not 4, right? So I'm going to throw 4 out. Even though 4 was a critical number from when we set the derivative equal to 0, we are not doing that. Do you understand we did this already, right? I'm not showing that work?
Yes.
Okay. So I'm throwing out 4y. It's not in here. You can only have a critical number be in the domain, and I've restricted it. All right. Now, step 2. I'm going to evaluate the derivative, evaluate the original function at the critical number. So I'm going to take the original function f, and I'm going to plug in 0, right? Isn't that nice? What's f of 0? 0, right? F of 0 is 0. Plug in 0 in that function, you get 0. All right, that's step 2. Step 3, evaluate at the endpoints. So now I'm going to plug -1 into this function, and I'm going to plug 2 into this function. -1 cubed minus 6 times -1 squared. That should give me -1 minus 6. I get -7. And then when you plug in 2, 2 cubed minus 6 times 2 squared, 8 minus 24. Y'all getting the same thing there? 16? Negative 16? Negative 16. Understand? And then step 2, we had what? 0? Okay. Step 4, compare the answers you just got. The biggest number you have is your absolute max. The smallest number you have is your absolute min. So what is our absolute max here? 0. That's the biggest number we have, right? That's the absolute max. What's the absolute min? Negative 16. Do y'all see how that works? Let's run through it again. I give you a function. It's continuous, right? Polynomial, on a closed interval. I ask you to find the absolute max and min. I use the closed interval method. The first thing I do is I find the critical numbers. Now, we already had shown that work, so when we do a new example, there will be some more work we have to do, right? Find the critical numbers, make sure those numbers are in the domain, throw out any ones that are not. Then, step 2, plug that number, those numbers, if there's more than one, plug more than one in here. Plug them into the original function and see what you get. Then plug in the 2 endpoints, see what you get, compare them, and the biggest one's your max, smallest your min. Now, to verify that, visually what we've done is what I'd like to do is I'd like to go to Desmos and graph this. Y equals x cubed minus 6x squared. And then if you want to do an interval in Desmos, you put a bracket, or sorry, a brace. We're going for what, -1 to 2? -1 less than or equal to x less than or equal to 2. All right. So if we take a look at that polynomial function and we restrict it between -1 and 2, you can see that we have an absolute maximum value of 0. That's the highest this ever gets, right? 0. And it happens where? At 0, right? 0 goes in, 0 comes out. So that's kind of like an ordered pair, right? X, Y. And then we have an absolute min right here. What's the absolute minimum value? -16. Where does it happen? At 2. So you can look at that as a point as well. On a test, if I ask you for the absolute minimum, if you give me the ordered pair to -16, I won't penalize you. All right? I actually prefer the point because it tells me when it happens, like where it happens as well. But if you just put -16, that's fine. Do you understand the idea?
Yes.
Okay, let's do another example. What do you think is going to start getting harder? This is what's going to start getting harder, right? The derivative is going to be something that's going to be harder to solve and figure out where it's 0 and where it doesn't exist. But the concept is pretty straightforward. If you can figure out where the derivative is 0 and undefined or not exist, plug those numbers, make sure they're in the domain, plug them into the original function, plug them to endpoints, you're in business, all right? All right, let's do this one. Ready? Find the absolute max / min of f of x equals square root of x minus 3 on the interval. Let's go with 4, 12. Ready? All right, first things first. I'm going to use closed interval method, right? Closed interval method. Well, I need to make sure I can use it, right? So is this a continuous function?
Yes.
Well, not everywhere. On that interval it is, though, right? Because if you plug in 4, is this defined? Yes, if you plug in 12, is it defined? And any number in between, it should be defined, right? So you should be good there. It should be continuous on that closed interval. Yes?
But when we plug them in, would we have to get the plus and minus?
No, because we never took a square root on both sides. You only ever get plus or minus if you take a square root. Right? We know we're not taking a square root. It's presented to us like that. It's called the principal root, which is just the positive root. Okay? All right, closed interval method. All right, so the first thing I'm going to do is what? Find the critical numbers, right?
Get the derivative.
So I've got to do all this work this time. Find the critical numbers. All right, so I'm going to need the derivative, right? Let's take the derivative of this. The derivative of this, well, 1 over 2 square root of x minus 3. That's it. That's our derivative, right? A little bit of chain rule there, but when you take derivative of what's inside, you just get 1. That all right, everyone? All right, so we've got the derivative. Now, what do we do with that derivative? To find critical numbers. Figure out where it's 0 and where it doesn't exist. So let's do the first one. Where's this thing 0? So the first thing I'm going to do here is I'm going to ask myself, where is this derivative equal to 0? Still in number 1, yeah, we're still trying to find the critical numbers. So where is this derivative equal to 0? Well, to figure that out, set it equal to 0, right? And now we've reached a critical thing that I want to make sure everyone here understands. All right? Side note. If you're ever given a fraction, doesn't matter what the fraction is, and you ever set a fraction equal to 0, right? All you really have to do is then ask yourself, when is the top 0? Right? I mean, anytime you have a fraction and you're trying to figure out where is it 0, all you really have to ask yourself is where's the top 0? And the reason why is because if you have this expression, couldn't I always multiply both sides by b here? And what would happen here? They go away, and what's 0 times b? Still 0. And so this just turns into a equals 0, right? So anytime you have a fraction, we have a fraction equal to 0, right? All you have to ever ask yourself is where's the top equal to 0? So this turns into you asking what? When is 1 equal to 0, right? And that's never going to happen, right? 1 is never going to be 0, which means that that will never be 0, right? This will never be 0, which means that you do not have a critical number so far. You don't have any critical numbers, all right? So far. We have to check now. So I'm going to say here, well, nothing. I just don't have anything from this, right? This basically doesn't happen. But I have a second thing I have to look at. The second thing I have to look at is where does the derivative not exist? So now let me just look at that derivative again. And let me ask myself if this ever does not exist. Does that ever not exist?
When x equals 3.
If x is 3, we're going to have a problem, right? Do y'all see in the bottom we get 3 minus 3 under there would give us 0? So potentially 3 is a critical number, yes? But,
Oh, but
it's not in the domain. So you don't need to consider 3, right? The only other things that would cause a problem here is if this was negative, right? Imagine that this thing was negative. Then you'd have a problem with the square root, right? Like if that x minus 3 was ever negative, you would have an issue, right? This would be bad. That'd be a bad situation, right? If this under here was ever a negative number. Well, if you just add 3 to both sides, then you're saying it's going to be bad if x is ever less than 3, right? You're going to have a problem with the derivative if x is ever less than 3. But again, in our domain, it's not in there, right? So do we ever have a problem with this happening? No. So this never happens, and this never happens, which means we have what? No critical numbers, right? No critical numbers. Yes? No, the endpoints are going to be checked in the next step, though, right? A critical number, by definition, is anywhere where the derivative is 0 or doesn't exist. All right, y'all good with step 1? We have no critical numbers. So our conclusion here is none, right? We don't have any. What's another way I could say none?
0.
No, I could say that, right? Empty set. I was saying, hey, throw all your critical numbers in this basket. What's in the basket? Nothing, right? Empty set. All right, what's the second step of the closed interval method? Right? Evaluate f at the critical numbers, right? I don't have any. Don't have critical numbers. I'm just going to start putting Cn from now on because I don't feel like writing critical number over and over. Don't have Cn. Third step, what? Evaluate the function at the endpoints. That I can do, right? That I can do. So I'm going to evaluate at 4 and evaluate at 12. And I think I made this so it'll work out nice for you here. Square root of 4 minus 3, square root of 1 is 1. And then square root of 12 minus 3 is 9, square root of 9 is 3. So what's our absolute max? 3, min, 1. All right, we good? Shall we see it real quick in Desmos? May as well. Square root of x minus 3, but we're restricting ourselves between 4 and 12. Go to the standard graph, zoom out, there we go. I think it's pretty obvious there that the max and min, max, right, are happening at the two endpoints. Kind of a boring function, but I wanted you to see a scenario where we don't have any critical numbers, right? I mean, okay, we didn't have any, fine, great. All right. Time to turn the screws. Let's do something